So the first thing is I added, oh, don't tell me this won't work. Okay. I wanted to just show a fluidized bed. Let's see if this works. Here we go. Okay, there aren't a whole lot of great images of fluidized beds, although maybe the number is slowly growing as we get more people taking YouTube videos of many things. But wasn't that amazing? They put water up through that bed of sand, and now all of a sudden, it's a very different thing. So that's one fluidized bed, and then here's one more. This one is even more fun, courtesy of YouTube. So this is a bed of sand that is fluidized with air. And if you've never seen this with your eyes or felt it with your fingers, you're like, what is going on here? And what happens in a fluidized bed is the fluid pressure pushing up on the fluid on the bed from the bottom exactly matches the weight of the media, the sand, per unit area. So that the pressure pushing up exactly matches the weight divided by the area, which is a pressure pushing down. And so each sand grain, or whatever the media is just kind of like hanging out there in what the sand grain experiences as being in perpetual free fall. It's at its terminal velocity because the fluid is coming up fast enough to hold it there. And so you get this very different material that acts like a fluid instead of like a solid. And you can move your hands through it easily. The video that I showed also has a clip of Mark Rober, the YouTuber, sitting on top of his spa filled with sand, and then they turn on the aeration system so that it fluidizes, and he just sinks into the sand when it fluidizes. So that's what we're doing inside filters when we backwash them. We are fluidizing the sand, and then the sand grains are moving around, and the flocks that were caught in the pores of the sand grains are knocked off, released. And so we end up getting a clean filter again, and we can start the process over. So today, now that we've seen fluidized beds, I want to go over some concepts that are important for understanding how filters work, ranging from porosity, sand size, the head loss, how much pressure drop there is as a fluid moves through porous media, and how much fluid do you have to push up through a sand bed in order to fluidize it. So we'll do the math for that, and you can actually, what's lovely is it's a relatively straightforward calculation to get a very good estimate of that. And then we may or may not get to this today, but there's then this big question about, well, what was the problem that Agua Clara was trying to solve when we invented the stacked rapid sand filter? And it's about the backwash dilemma of how in the world do you backwash a filter if you don't have access to electricity? And so that was what drove our design process. The first, porosity. So porosity is pretty simple. It's the volume of the voids that are created by the sand grains divided by the total volume. So volume of voids over total volume. And so as a little example, if you've got a cubic meter of dry sand, dry aquifer material, and you weigh that, and it ends up weighing 1,600 kilograms. So you've got a cubic meter, it weighs 1,600 kilograms. And then you have it in a tank, and you put water in until it's completely saturated with water. And you weigh it again, and now it weighs 2,000 kilograms. So the first question is, what's the porosity of the aquifer material? What fraction of the aquifer material was actually voids where there was air. And conveniently, we can just forget about the mass or the density of air. It's close to zero relative to water, so we can ignore that. And what we did is we went from 1,600 kilograms of aquifer material to 2,000 kilograms total. That means there's 400 kilograms of water in the pores. And 1,000 kilograms of water in a meter cubed would be, that's the density of water, right? 1,000 kilograms per meter cubed. So 400 kilograms out of 1,000 kilograms total is the ratio of the void volume. So the void volume or the porosity is 40%. Does that make sense? If we had filled that whole container up with water at a cubic meter, it would have been exactly 1,000 kilograms. We were able to put 400 kilograms worth of water in there. So it's 400 over 1,000, it's 0.4 is the porosity. And by the way, that's kind of the standard accepted porosity. It varies a little bit, but if you have a well-graded material of uniform size, that's roughly what the porosity is. What about the bulk density of the aquifer material? So this word bulk just means that it's kind of like the density that you get when you dump a load of it there. You know, you have your dump truck and you dump a load of it, and that bulk density is your dump truck held, I don't know, 10 cubic yards, and this was how much it weighed. If you take that weight in kilograms and divide it by a volume in cubic meters, that's the bulk density. So the bulk density includes the fact that material had some voids, and you're counting those voids as volume of the material. So the bulk density of this aquifer material, it weighed 1,600 kilograms, and it occupied a cubic meter. And so its bulk density is 1,600 kilograms per cubic meter. That one's easy. Bulk just means the whole thing, including the pores. And then, but we're also often very interested in what's the actual density of the aquifer material. So if it's sand, what's the actual density of the sand when we don't include the pores? And so this is a little more complicated. We have to figure out first, how much sand was there? Anybody know how many cubic meters of sand we actually had? We had 1 cubic meter of pores plus sand. We had 0.4 cubic meters of pores. So we have 0.6 cubic meters of sand. And we also know how much those 0.6 cubic meters of sand massed, what their weight was. It was 1,600 kilograms. So if we take those 1,600 kilograms and divide it by 0.6, the actual real volume of the sand grains, we get 2,700 kilograms per cubic meter. And by the way, I, of course, set this up so that it made some sense. The actual density of silica sand is around 2,650 kilograms per meter cubed. So that's what I was talking about here with this aquifer material was mostly like quartz sand, or silica sand. Next question. Which of these materials will have the greatest porosity? 1 micrometer diameter clay, 0.2 millimeter diameter sand, or 1 centimeter diameter gravel. And to make this as simple as possible, you can just pretend for a little bit that each of these is spherical. So we've got spherical clay plates. They're not plates anymore. They're little spheres, a micrometer in diameter. Same with sand and gravel. Which of those has the greatest porosity? If they're spheres, they're all the same. I think it's very easy to confuse porosity and another idea, which is hydraulic conductivity, or how easy is it to push water through this? So if I had asked you, which one of these is it easier to push water through, then the answer is clearly gravel. But the void volume could actually be almost the same for all three of these. The void fraction could be almost the same for all three of these. Okay, but there's some fun results of this. If you were given some of each of these materials, how could you make something that had really low porosity? And we're not going to bother going through all the math to figure out exactly how you would do this. But can you think about, like, how would you mix these three materials together to get something that in the end has a much lower pore volume?